Alright, this is the very last RC circuits video that I'm going to make. This one discusses a slightly different example circuit, which I have drawn for you already. So what I want you to notice is that this time I have two resistors, which I've named A and B. For simplicity, I'm going to say that they have the same resistance. They're identical. And I just gave them these names so I could easily refer to them. But they wouldn't necessarily have to be equal, obviously. They could be different. So when the switch is first closed, the system will begin to charge. So we're assuming that there's nothing on the capacitor right now. But if I close the switch, current's going to flow out of the battery. Some of that current is going to go down path A, and some of that current is going to go down path B. And so it's the current that goes through path B that will charge the capacitor. The other current is just going to return to the battery without interacting directly with the capacitor. Eventually the capacitor is going to fill up, whatever full means in this case. We'll get to that. And when the capacitor is full, current should stop flowing through the capacitor. But even if current stops flowing through that branch, through branch B, current is still going to flow through branch A because there's not a capacitor there. So even if we disconnect, the capacitor side because it's full, current is still going to flow through resistor A in that case. So the questions here are about the initial and final values and the time constant for the circuit. We don't need to do anything with the exponential functions here, and that's often going to be the case, even in questions from the College Board. Many times, all they really want to know is if you remember those rules of thumb about how the empty capacitor works and how the full capacitor works, and how they impact the circuit around them. So for the initial values, the important idea here is that the capacitor basically is like a wire. Because at the beginning, the capacitor is empty, and an empty capacitor freely allows current to enter because there's no charge built up yet, and so there's no electrostatic force repelling the current, stopping it from coming in. So, if I think of the capacitor as just being a wire, I know that the total resistance of the circuit is effectively going to be half R, where R is the resistance of these two identical resistors. We'll just let them both be called R. Since they're identical and they're in parallel with each other, if you go through the whole reciprocal adding process, you're just going to get half. Similarly, if you had like 3 identical resistors in parallel, it would be 1/3 R. If you had 17 of them, it would be 1/17 R. As long as they're identical, it's very simple. So in that initial moment, the effective resistance of the circuit is half R. That means that the current comes out of the battery is going to be E over half R, which would be 2E over R. If that's the amount of current coming out of the battery, then the current going down each branch is going to be half of that. Since the branches have the same resistance, they will share the current equally. So IA, for example, is going to be E over R. IB and IC are also going to be E over R. I could also use those currents to calculate the initial potential differences for the resistors. since the potential difference of a resistor is always I times R. So both of the resistors have initially a potential difference of E. So delta VA, delta VB, those are both E. Delta VC is 0, because the delta V for a capacitor is based on the amount of charge, and at the beginning the charge of the capacitor is 0. So that's all the initial stuff. In the final case, which is often called either this is often called the steady state, because if you wait long enough, the system stops changing. It reaches some fixed static state, so I call that a steady state. After a very long time, aka an infinite amount of time, the capacitor essentially becomes a break or a gap in the circuit with no current. So when that happens, the right-hand branch of the circuit, branch BC, I can basically just pretend it's not even there. Nothing is flowing through that anymore. So the effective resistance of the circuit in that case, as seen by the battery, is just 1 R. The only relevant resistor is resistor A. That means that the current coming out of the battery is E over R. So it's producing less current than it used to, because the resistance has gone up. The initial resistance was half R, and the final resistance is twice as much. So the battery is producing less current now. Delta V for resistor A is going to be, whoops, I don't need that R there. It's going to be E, because it would be the current E over R times the resistance R works out to be E. So delta V for resistor A has not changed. Delta V for resistor B is going to be 0, because there's no current flowing through resistor B. And delta V for the capacitor is going to be E, because the capacitor is full. So if the capacitor is full, its potential difference has to be equal to the potential difference of whatever it's connected across. In this case, that's the battery. I can justify those potential differences with a loop rule as well. So I'm going to do a green loop for resistor A, like this. So if I write out that loop, I would say 0 equals E minus IR. Actually, I don't even need to say IR. I can just say delta V A. Let me just get that cleared. So therefore, delta VA has to be E. But for the other ones, I'll do a blue loop like this. That loop is going to be 0 equals E minus IB times R minus delta VC. But the current through resistor B is 0. So because that current is 0, delta V for resistor B is 0, which I wrote earlier. And therefore delta V for the capacitor must be equal to the EMF. Since I know the delta V for the capacitor, I could also write the charge. Q has to be delta V times C, and the delta V was E. So the final charge would be EC. Now, the other thing this asks about is a time constant. While discharging, I haven't talked about the discharging case yet. I should do that. So far I've only been thinking about the charging case. So I closed the switch, let current flow to charge up. The time constant during charging is going to be very tricky to figure out. And the College Board would not ask you to figure this out. The reason it's so hard, charging tau equals hard. The reason that the charging time constant is so hard is that the effective resistance of the circuit is changing. I already covered that, right? The initial resistance is half R, but then the final resistance after a long amount of time has passed is different. So that means R has to be a function of time here, which means that solving the differential equation is going to be different. The differential equation we set up before only had I and Q as functions of time. If R is also a function of time, much more complicated. So finding that charging time constant is not easy. Would require a different approach. However, if the system is discharging, so once we've reached that like steady state where the capacitor is full, if I were to open the switch and let the system discharge, it's pretty simple then. So in the discharging case, I'm going to write the answer first. Tau is going to be 2RC. I've run out of space. I'm just going to choose another color. I'll use orange. No, purple. So my diagram's going to get kind of busy. I'm going to draw some pluses and minuses on the capacitor. That's the way the charge looks once it's full. And then what I'm going to do is put the switch back into the open position. So that removes the battery from the circuit. And that means that the circuit is now the capacitor and the two resistors. I'm going to draw a purple arrow to show the current. The current is going to flow counterclockwise from the positive plate back around to the negative plate. And you can see that that current has to go through both resistors. So the effective resistance here is now 2R because the resistors are in series with each other in this arrangement. In the charging process, they were in parallel, at least at the very beginning. As soon as the capacitor starts charging up, then A and B are not in parallel anymore because there's this other object, C, on one of the paths. But in the initial state, at least, A and B were effectively parallel to each other. But now that we've changed the switch, A and B are in series with each other instead. So the total resistance of the discharging circuit is 2R. The capacitance of the discharging circuit is C. And that's where this time constant of 2RC comes from while discharging. Again, the charging case is pretty complicated. Even if you take intro physics again in college, they won't ask you to do this in that class. If you take like a dedicated electronics course, as a sophomore or something, you'll run into it then, but you would not run into it as a freshman. So obviously a problem like this could have numbers in it. I think the AP test this year is probably not going to have any numbers because that would make it too easy to plug things in to various websites or software and get answers. So it's probably going to be almost all symbolic. But this is an example of a slightly more complicated circuit than the one I started with. The problem set that I'm assigning has a bunch of other RC circuit layouts, again, that you'll have to think about kind of along these lines, where often it'll ask about the initial and final values. Occasionally, you'll have to do some random point in time, making use of those exponential functions. But notice for this example here, I didn't use the exponentials at all. And that's going to happen, pretty often, at least half of the time. They don't care about the transient behavior. They only want to know the starting and ending behaviors. So that's it. I hope that this was useful. I hope that it made some sense. Please come by my office hours on Tuesday or Friday if you want to go over any of this, or if you want help with the problems.